Thank you, IAPT RC1, for giving me this opportunity to interact with our teacher colleagues. Am I audible? I hope.
Yes, sir. Yes, sir. You're perfectly audible. Please.
Yeah. So I will also would like to acknowledge IAPT Mumbai, where we have been conducting various kinds of workshops, and what I'm going to talk and share with you is outcome of that. Also, my friend Dr. Atul Modi, with whom I have interacted many times. So this is out of that. So let us talk about, we are talking about building competencies in scaling and order of magnitude estimation. And in the earlier talks, the sir was talking about the student getting confidence into, and as well as along with students, even teachers, getting confidence into handling the real life situation. And this is one particular skill where it is going to really help teachers in the first place and students eventually to get kind of confidence to handle the real life problems. So I'm just starting with a small quote from surely you're joking, Mr. Feynman. So here he mentions about his experience, how he started learning from his father in his childhood. So he has written, we had an Encyclopedia Britannica at home when I was a small boy. He used to sit me on his lap and read to me from the Britannica. We would be reading and say about dinosaurs, and it would be talking about something like, say, T-Rex. And it would say something like that encyclopedia entry, that this dinosaur is 25 feet high and its head is 6 feet across. Now, my father would stop reading and say, now let's see what that means. That would mean that if he stood on our front yard, he would be tall enough to put his head through our window up here. So, and he mentioned further that we were in the second floor, but his head would be too wide to fit in the window. Now, he is talking about the numbers the numbers which are mentioned here, 25 feet high and 6 feet across. What Feynman further comments is everything he read, that is his father read to me, he would translate as best as he could into some reality. And this is where one of the very important skill comes, that whatever numbers we are looking at, okay, how to make meaning out of those numbers. And we need specialized practice for working on those kind of things along with it, and the confidence comes slowly as you start working on it. So let's talk about some examples. Here I'll be sharing some of the examples and how we can slowly go on building up this kind of skill. What kind of problems can be given to students, what kind of problems we can design, and what kind of problems, even as a pastime activity you can work on, because ultimately the skill comes when you work on it for a long time. And why am I saying pastime activity is because many of these problems are either order of magnitude calculations, and nowadays with calculators available in mobile phones, and mobile phones are always available with us, any new idea clicks, okay, you can quickly do a small calculation. And though there are scientific calculator apps available in the mobile, even with simple calculators, some of these things can be done quickly. So let's talk about, I was talking to, recently I was talking to a group of students from class 11, and I just asked this question that, okay, what estimate the number of atoms in human body? I was talking about the 3D printing technology and how teleportation, different steps in teleportation can become possible in one of the popular level lectures. And then I said, okay, let us estimate number of atoms in human body. The first question I asked is, okay, what is the approximate mass of human body? So that, of course, people can answer, and you may approximate this as 100 kilogram or 50 kilogram. Of course, 100 kilogram is too large. But then idea here is, if I want to estimate the number of atoms, okay, my answer may change at the most by 2 times. Okay, so based on our assumption, the final answer will change by half. If I take 100 kilogram, it will be double, or if I take 50 kilogram, then I'll get some number. So this number is not really going to be very important, because surely we are not going to go something down to 10 kilogram or something up to something like 500 kilograms. So this order of magnitude is perfectly fine. Next question, what we need to bother about is which atoms are there in human body. Now there are large number of different kind of atoms, but which is the most abundant? And one answer which many students gave is, because that is what we talk about and we emphasize in biology, that it is all carbon-based life. This is a carbon, but without realizing that 70% of our body is water, and there are 2 atoms of hydrogen in every molecule. So lighter atoms will be the most abundant, and that will dominate in our count. So we have to keep that in mind when you are talking about, say, number of atoms in human body. And 70% is water, and then you can talk about the average density is close to water for human body. Okay, so hydrogen becomes most abundant atom. And then what is the mass of hydrogen atom? Okay, now of course a good physics student should know what is the mass of hydrogen atom. That is one thing. Okay, but many times what happens is, I mean, this is what I have observed at multiple places. Students don't remember mass of hydrogen atom, but if you ask them what is Avogadro number, I have seen everywhere people have remembered Avogadro's number. 6.02 10 to 23 is what they will say, without realizing that reciprocal of that is mass of hydrogen atom. So if you use an SI system of units, then it is kilomole, and then it is 6.02 into 10 to 26, and reciprocal of that 1.67 into 10 to minus 27 kilograms. So that's mass of hydrogen atom. And then it becomes easy to calculate that you are talking about something like, say, 100 kilograms. If I say 10 raised to 2, and then I'm dividing that by mass of 1 hydrogen atom, which is of the order of 10 raised to minus 27, and then I get approximate number as 10 raised to 29 atoms are there in human body. Now this was a simple example, but starting with these kind of things, surely we can make them do simple, small order of magnitude kind of calculations to get an idea about the numbers that one handles. Now let's talk about, say, estimate the total mass of atmosphere. Okay, how does one do that? So everybody knows mass of Earth. Okay, I mean, generally those are written and many people remember that. But suppose I want to estimate the total mass of atmosphere, what will I do? So which principle will I use? Now, one of the principle which can be used is, we know atmospheric pressure, and we can estimate the surface area of the Earth, because radius of the Earth 6,400 kilometers is what many times people remember. And then you can do the calculation that what is 4 pi r square, and you can get that number. So that will give you the gravitational force by atmosphere on the Earth. So you have atmospheric pressure, which is about 1 bar, approximately 10 raised to 5 pascals. And then the surface area 4 pi r square, and r so that surface area multiplied by pressure gives you the force, and this force is nothing but gravitational force of atmosphere. It is weight of the atmosphere. And one additional assumption you will have to do, since the atmospheric height is very small as compared to the radius of the Earth. Atmospheric height is how much? It is about we say about 10 kilometers. Surely it doesn't go beyond 100 kilometers, and as you go up, of course, it starts becoming less dense. So mainly dense atmosphere, if you consider, it is about, say, 10 kilometers or so. And then you can assume that when you go distance at 10 kilometers, okay, as compared to 6,400 kilometers, which is radius of the Earth, the G is not going to change much. The gravitational acceleration is not going to change much. And then you can say that, okay, I will use value of G as, say, 9.8 or 9.8 meter per square second, or say, even I can approximate, because I'm estimating 10 Newton per kilogram or 10 meter per square second. Now this will give estimation of mass of the atmosphere. So what you've done is you have calculated the atmospheric pressure, which is 10 raised to 5. Then you are multiplying with 4 pi, which is approximately 10, and into r square, so 6.4 into 10 raised to 6 meters square of that. And then you can see that that value 6.4 square can be approximately 40, okay, and into 10 raised to 6 square, so that will be 10 raised to 12. And then you have 4 pi, which you have approximated as say 10, And so effectively you get something like 10 raised to 12 into 10 into 40. So that is about 4 into 10 raised to 14. And then you multiply with 10 raised to 5. So that gives you something like 10 raised to 19 newtons, and you divide by 10. So that you get approximately 10 raised to 18 kilogram as mass of the atmosphere. So 10 raised to 18 kilogram, you see, is very small fraction of 10 raised to 24 kilogram. So, but this is how one can estimate the mass of atmosphere. You can also go for more such kind of problems of estimating the amount of radiation by human body. Okay, where no students have learned about Stephen's law. So Stephen's law is applicable for black body radiation. Okay, now can you assume that human body is a black body? Now, apparently not a perfectly black body, because whatever light is reflected on us, part of that gets reflected back. Okay, so we know that human body is not a perfectly black body. So, but there will be some particular coefficient, okay, that we will have to talk about. Now, that coefficient will give limitation on the net power given. Okay, but at the same time, we have to see that the amount of reflection that our body is going to do, or amount of absorption the body is going to do of whatever radiation falling, okay, that same coefficient probably will also play a role in giving out the radiation. So if I assume that it is a perfectly black body with small correction, then the power given according to Stephen's law is sigma T raised to 4 into the area. Okay, because it is the amount of power given out, amount of energy given out per unit time, per unit surface area. Okay, so that we talk about is, okay, there was a question, but I'll answer that question immediately after this. That we are talking about sigma T raised to 4 into area. And sigma is easy number to remember, 5678, 5.67, 10 raised to minus 8 SI units. Our body will be emitting with temperature T1, which is at higher temperature, 37 degrees Celsius, easy number to remember, 310 Kelvin, because we have to write everything in absolute temperatures in this particular law. Also absorbing from surrounding temperature. So surrounding temperature we can approximate to 27 degrees Celsius. Okay, of course that changes, but say if I assume 27 degrees Celsius, then I know it is 300 Kelvin, easy for calculation. And then the power can be calculated using this. Now, one estimation here required is how much is the area of the human body. And that is an interesting question, can be asked to students, and students come out with very interesting ways of calculating. When I tried at multiple times with students, some of them assume human body as a cylinder, some of them assume one cylinder and a sphere on top of that, something like that, or part of a cylinder and then two cylinders for leg and then sphere at the top. Doing all this, okay, considering the say for example, if you're talking about the circumference is something like say 36 inches, then you can convert that into centimeters. It could be 90 centimeters, and then 2 pi r is 90, and accordingly you can calculate r, and then basically 2 pi r is what is important, because for the cylinder it is 2 pi r into height. Okay, and when you do that, the area, surface area, turns out to be about 1.5 square meter to 2 square meter, approximately around that. And then after doing this calculation, effectively the power turns out to be something like 100 watts. What does it mean? 100 joules energy we are emitting per second. Now, is it a meaningful number? So it turns out to be, yes, it is meaningful number. In multiple ways we can check that. Let me quickly write things on this. So we are doing this calculation. Just a minute. Let me just add a slide here so that I can write on that. Okay, so I wanted to do this sigma 310 raised to 4 minus 300 raised to 4 into area, and I said calculating all this number, this is approximately say 100 watt, which is 100 joules per second we are emitting. Now in one day, there are approximately it is exactly 86,400 seconds. This is actually exactly, not approximately, but this is approximately 10 raised to 5 seconds, which means total amount of energy you give is 10 raised to 7 joules per day. Total amount of energy given out, 10 raised to 7 joules. And if you could calculate this into calorie, then we know that 1 calorie is 4 joules. And this would, and 1 kilocalorie will be about 4 into 10 raised to 3 joules. And when you divide this by say 4 into 10 raised to 3 joules, this is the conversion factor effectively for kilocalories, you get number like 2,500 kilocalories. That is what we typically say is the amount of energy required, 2,500 kilocalories, the amount of energy required through the diet. Okay, so effectively what you are going to eat, all that energy, we are going to do less amount of, effectively the mechanical energy is less, but total amount of energy that we are giving out is effectively the same order of magnitude. Okay. Okay, let me just see. I think there was some, yeah. So basically, this is what we say. And then if somebody is doing extra mechanical work, then there are multiple factors taking into it, and then amount of energy, the energy consumption required will be higher. So there are different ways of looking at it. Also, we can say that because every person is effectively like 100-watt bulb, amount of energy given out. Say if 50 people are sitting in a room, okay, you really need good amount of ventilation or at least fan working, because otherwise it is something like 50 into 100, that is 5 kilowatt heater going on. And that immediately students are able to connect that, yes, why you need the good ventilation when large number of people are sitting in a small room. Coming next to other kind of things, but let me just go to the question, some comments over here. Explain the conversion of power of temperature from power 4 to power 2. Okay, let me see whether this was a typing error. This was a typing error. I'm sorry for that. Let me just change that. This is typo error. Thanks for pointing out. So is my screen visible?
Yes, sir.
Yes, sir. Yes.
Yeah. Thank you. Okay, now coming to another kind of question, like when people talking about the current flowing through the metal and the amount of we know if you take small amount of material, we know we are talking about moles, which is of 10 raised to 23 atoms. But how many electrons are actually contributing to the current? So suppose I am interested in a simple case, the laboratory kind of case. A 10 milliampere current is flowing through the wire of thickness 1 millimeter. Okay, 1 millimeter thickness I have taken for easy calculation, but it is also close to 22 gauge wire, which is 0.7 millimeter, and 18 gauge wire, which many times 22, 18 gauge wires we use in the laboratory. If you're talking, I'm talking about single stranded wire. Okay, and then 18 gauge wire has 1.2 millimeter thickness. So I'm taking somewhere order of magnitude. How many electrons are moving per unit time per square angstrom? I'm saying square angstrom. Why? Because typical size of atom is an angstrom. So when you consider one particular atom, how many electrons are effectively flowing? That we want to calculate. Sometimes these numbers can be calculated just out of fun. I mean, you may not really make big application, but this gives you some good idea of the order of magnitude that is happening at this level. So 10 milliampere current is same as 10 millicoulomb charge flowing per second, and 10 millicoulomb charge is 10 into 10 raised to minus 3 coulomb divided by charge on 1 electron. So basically it is 6.25 into 10 raised to 16 electrons flowing. Okay, but that is those are the total number of electrons flowing through the entire thick wire. Now, through 1 millimeter thickness, we have typically pi r square. If you consider 1 millimeter thickness is actually diameter. So if I take pi r square, then this is the 0.78 square millimeter. And when I convert that into angstrom, 1 millimeter is 10 raised to 7 angstroms. I get a number like 7.8 into 10 raised to 13 square angstrom. So that 1 millimeter thickness wire, if I consider the area of cross section in terms of square angstrom is this. And then 6.25 into 10 raised to 16 electrons moving per second per this much area. So per square angstrom, it is going to be about 800 electrons. Okay, so you see that about, you consider one particular atom, okay, about 800 electrons per second are flowing across that. Okay, this is one. I mean, this gives some interesting idea to students, at least at order of magnitude level, that how many electrons are flowing. To give some basic idea, this of course later can be taken for statistical analysis and those kind of things. But this inquiry into the numbers becomes very useful skill, and that can be developed right from the secondary school level. Another area which can be interesting to students is scaling. So if the sun is of the size of, say, 1 rupee coin, at what distance Earth will be placed? Now this becomes a good scaling model, especially the astronomy becomes a really good scaling model, or the atomic level physics also becomes a good scaling model. So sun is of the size of, say, 1 rupee coin. Now we need some amount of information that at what distance the Jupiter will be placed and at what distance the nearest star will be placed. We want to do these kind of calculations. So here what we can do is, let's work out some simple calculation, work out some calculation over here. 1 rupee coin, if you look at it, the radius is about 1 centimeter. So radius for is approximately 1 centimeter. And what is the radius of the sun? So either, of course, you can directly take information that it is about 7 lakh kilometer radius, or you can make an estimation that the 1 AU distance, that is Earth Sun distance, is about 1.5 into 10 raised to 11 meters, and the size of the sun is half degree. The diameter of the sun is half degree. 1 degree is approximately 1 by 60 radians. Actually, it is 1 by 57, but order of magnitude 1 by 60. So this is going to be about 1 by 120 radians, approximately 1 by 120 radians. This is diameter. Okay, and the radius is going to be 1 by 240 radians. Now, the advantage of radians is, how does one define radian? Radian is the arc length upon radius. So straight away you can find out how much is this going to be. That is what we say, that the arc length is given by r into theta, and now this is 1.5 into 10 raised to 11 multiplied by 1 by 240, because theta is 1 by 240 for radius. Okay, and this you can then calculate approximately, I mean, as say 7 into 10 raised to 8 meters. So what you are doing is 1 centimeter, you are now scaling up to 7 into 10 raised to 8 meter, you are scaling down to 1 centimeter. Okay, and then at what distance Earth will be placed? So that is the question. Now we know here directly from this that Earth is effectively placed at 120 times the diameter, and therefore Earth will be placed 120 times the diameter of the sun. The diameter of the sun will be 2 centimeter, because the radius of 1 rupee coin is 1 centimeter. So 2 multiplied by 120, that is at about 2.4 meter, Earth will be placed. So you have, I mean, you can imagine then, now a coin is here, and at around 2 meter distance, 2.5 meter distance, the Earth is going to be placed. What will be the size of the Earth? That will be 100 times smaller than size of the sun, approximately 100 times smaller. Similarly, you can find out at what distance Jupiter will be placed. Jupiter is 5 AU distance. That is what is written in the book. So 5 times 2.4, you can calculate, and accordingly at that distance, okay, about 12-meter distance. So at 12-meter, students can imagine how long is 12 meters. Okay, 2.5 meters, students can imagine how long is that, and they can imagine, they can see directly what is the size of 1 rupee coin. So this gives them some interesting ideas to imagine, okay, and look at how far the objects are placed within the solar system itself. And then you can of course calculate at what distance the nearest star will be placed. So here you are scaling down. Even if I consider this 7 into 10 to 8 as approximately 10 to 9, okay, I'm going something like a billion times smaller model I'm making. And if the nearest star is something like 4 light years away, so 4 light years, when you convert into meters, it is 4 into approximately 10 to 16 meters. And my scaling factor is of the order of 10 to 9 now. So when I divide by 10 to 9, okay, I'm going to get number which is something like 10 to 7. Okay, so 10 to 7 is, and in terms of what I have to do in terms of 1 rupee coin, I have to talk about. So 1 rupee coin was considered to be 1 centimeter. So 10 to 7 centimeters, that is 10 to 5 meters. That is about no, sorry, 10. I 10 to 7. I have to so 10 to 7 meters I will have to keep. Okay, and you can imagine 10 to 7 meters is how much distance? That is about 10,000 kilometers. 10,000 kilometers. So idea involved here is that sun is at one place. Okay, the nearest star is going to be at very long distance, and that distance is of few thousand kilometers. And few thousand kilometers, when you're talking about, it means there is a lot of empty space in between. Now, this can be connected to my next immediate slide, where you are talking about scaling of galaxies. So if you now consider the Milky Way is of the size of 1 rupee coin. So one Milky Way's diameter given in the books is about 100,000 light years. Okay, 0.1 lakh light years or 100,000 light years. Find the distance at which the nearest galaxy is placed, and we know the nearest large galaxy is Andromeda galaxy, which is 2.2 million light years away, or 22 lakh light years away. So if the size of Milky Way is 1 lakh light year and the nearest galaxy is placed at 22 lakh light years, what it means is, if I take 1 rupee coin over here, 22 times the distance I will have to keep the next galaxy, which is very small. Okay, around a foot distance. Whereas within a galaxy, if you're looking at the position of the stars are really far off. So it means effectively a galaxy has a lot of empty space in between. And that gives them a good idea about, when they read something like the Andromeda galaxy is coming towards us, and another 3 billion years or 4 billion years, it is going to collide with our galaxy. It is not going to be collision between two balls, because the distance between galaxies is very small as compared to the size of a galaxy, but distance between stars is very large as compared to the size of the stars. So lot of empty space, and effectively the two galaxies are going to merge like a cloud rather than collide like a ball. So this can be of simple scaling calculations. Now you can also do calculation for scales at low temperatures. So what is the thermal energy of helium atom at room temperature? So you say energy is calculated as 3/2 kT, and you can then substitute the value of Boltzmann constant into the room temperature about 300 Kelvin, and then you get answer something like 6.21 × 10⁻21 joules. Okay, it is useful when you to convert these small energies into electron volt, and you get number something like 0.039 electron volt, because I've taken a factor of 3/2 over here. Okay, so it is like this. Many teachers surely must have remembered that kT is of the order of 25-26 milli electron volt, or 0.026 electron volt. So this is 1.5 times greater than that. Now, what is the momentum of such particles? So you apply momentum, no, energy is basically kinetic energy, half mv square or p square by 2m, and then you can get a value of something like 9.1 into 10 to the minus 24 kilogram meter per second. Now, typically when you are okay, number crunching is one thing, fine, but when you are talking about momentum at atomic level, typically you get this number, no, 10 to the minus 24 kilogram meter per second many times. So when you are doing a calculation, and when student has done calculation multiple times and he gets an answer of this order, then he should be comfortable. Okay, at least the order of magnitude seems correct. What next? What next is you can now calculate de Broglie wavelength, because they have been introduced to this concept of de Broglie wavelength. So the de Broglie wavelength, you know, is h by p, and you have calculated momentum, and the value of h is known, and that turns out to be 0.73 angstrom, smaller than size of atom. I have purposely taken helium atom because then we are not talking about multiple atoms in a molecule. Simple atom, and this distance is very small. So typically in a gas, each of them are not going to interfere with each other because the wavelengths are very small, and they are not going to basically interfere with each other. What happens at 1 Kelvin? So what you have done, temperature has gone down straight away by 300 times. Okay, the value will reduce by 300 times. The thermal energy will reduce by 300 times. And de Broglie wavelength, okay, it will increase by a root of 300 times, but root of 300 is 17 times. So, and you get 13 angstrom. Now, 13 angstrom is very large as compared to size of atom. And if you're talking about 1 Kelvin, probably all helium atoms will be in liquid phase, or they will be close together. Okay, and if they're going to close together, the wave functions are going to overlap, and then it will become a single quantum system. So whether I should deal with the classical physics, or should I deal with quantum mechanics? No, de Broglie wavelength ruling. So when the size or the distance between two particles is comparable to the de Broglie wavelength, then quantum mechanics is required. If it is, the distance is large as compared to de Broglie wavelength, the classical physics is good enough. So that idea can be given with these kind of numbers. One additional problem on this kind of category. So when a star is compressed, okay, the ultimate end phase of many large stars is, people learn, that is neutron star. So where all electrons and protons are pushed together to form neutrons. And size of a nucleus, student has learned, is about 10 to the minus 15 meters. Mass of neutron is same as mass of hydrogen atom, approximately this. So you can approximately calculate what is the density. So density is of the order of 10 to the 18 kilogram per meter cube, which should be meter cube. Okay. And then typical mass of neutron star is expected to be a few times mass of the sun. So generally it is given that if the core of the star is more than 1.4 times mass of the sun, Chandrasekhar limit, then it will become a neutron star. And it can't be more than about 3 to 5 times solar mass, otherwise it will become a black hole, the core of a star, when it is going to die. So it is just few times mass of the sun. So mass of the sun, we know, is 2 into 10 to the 30. So order of magnitude, let me just take that. And then when you take a cube root of this, because this ratio 10 to the 30 mass upon density will give you volume, cube root of that will approximately give you the size. And that size turns out to be 10 to the 4 meters, which is about 10 kilometers. So you see the neutron star typically will be of this order. You can do further inquiry into this, that when the star compresses by this much volume, and star is already rotating, like sun is also rotating. The sun takes about 25 days to go around itself. That angular momentum has to be conserved if it is not taken by other objects when the star is dying. So in that case, how fast it will start rotating, because that everybody talks about when things compresses, they spin faster. Okay, those conservation of angular momentum things we always talk about. We always talk about the rotating table experiments. Okay, but here we have got something huge system which is falling down by 5 orders of magnitude. So radius, when comes down to by 10 raised to 5 times, the moment of inertia will reduce by 10 raised to 10 times, and therefore the angular velocity will increase by 10 raised to 10 times. And then we can do calculation. 1 day is of the order of 10 raised to 5 seconds. And typically sun-like star is rotating with something like 25 days. Okay, so it is about 2.5 into 10 raised to 6 seconds, and now it is falling down by 10 raised to 10 times. So 10 raised to 6 divided by 10 raised to 10. Okay, that will effectively give you milliseconds. So you see the millisecond will be the typical time scale with which these neutron stars will rotate, and that is what you have observed in case of pulsars. The pulsars emit at milliseconds. So many times their rate of rotation is in the order of millisecond. So these ideas can be conveyed. The idea here is many of these calculations do not need very high level physics, and this can student can get a confidence saying that if I do these kind of calculations, I may be able to handle some big problems. I don't need to really learn a lot of theory for that, because this is a different kind of skill. Of course, there is always a question of a question where whatever I do, is it a correct thing to apply, or I mean, is some different physics involved? So it is perfectly fine that you may apply at times wrong wrong way. Okay, but unless until we work on these kind of things, it is generally going to be students will not be able to develop the skill. The whole idea of learning is make a mistake, and there will be people who will guide you. The same thing is applicable for teachers. At times there could be some amount of calculation mistakes can be very done, but conceptual sometimes some conceptual problems can come, but slowly the confidence starts building. Now here comes one or two surprising answers, so I'll just end with those. So suppose you compare this is actually a problem from Halliday and Resnick, comparing force on moon by earth and sun. So there is no estimation here. It is a straightforward comparison, but it gives surprising answers. The answer to the problem can lead to further inquiry. So say, what pulls the moon with greater force, the sun or the earth? So the sun moon force, we know we are applying law of gravity. So g into mass of the sun into mass of the moon upon moon sun distance square. Now moon sun distance is approximately same as earth sun distance, and then moon earth distance, moon earth force, okay, is g into mass of moon mass of earth upon the distance between earth moon square. And then you see, when you want to take a ratio, the common factors will get cancelled, and then the moon sun force upon moon earth force will be given based on this factor. Now you can put the numbers, and what you get is interesting number 2.2. What is this? The force on moon by the sun to force on moon by earth is approximately double. So sun pulls the moon with almost double the force than earth is pulling the moon. And then the inquiry can start, and then why moon is not going around the sun? And then you start saying, but moon does go around the sun. Okay, then what could be the orbit? And such kind of questions can be asked. I'm ending with this last example where I have purposely written this. Okay, that expansion of the universe wrongly applied at a smaller scale. This also is an interesting calculation. Okay, the results are surprising. So Hubble's law suggests that universe expands at 72 km per second per megaparsec. Okay, so if object is at 1 megaparsec distance, it seems to be going away at 72 km per second. If it is at 10 megaparsec, it is going away with 720 km per second, and so on. Now parsec is approximately 2 lakh astronomical unit. In fact, by definition, it is the tan of 1 arc second reciprocal. So it is 206265. And then 72 km per megaparsec. If I want per parsec, then I have to divide by mega, that is a million. So kilometer divided by million becomes millimeter. Okay, and then 72 millimeter per second per parsec. And if I want to convert that into per AU, per astronomical unit, it is I have to divide by this 2 lakh. So I know 1 second, 10 to 5 second is 1 day approximately. So basically, it is ultimately it will get converted into 36 millimeter per day per astronomical unit. Okay, so if an object is a 1 astronomical unit, the thing should move away at 36 millimeter per day. That means Earth should go away from the sun at 36 millimeter or 4 centimeter per day. That doesn't happen. Okay, But moon is about 1/380 astronomical unit, and there are about same number of days in a year. So moon must go away by about 30 to 40 millimeter per year, or 3 to 4 centimeter per year. And this is almost the rate at which moon is going away. So you see, now this is wrongly applied, but moon goes away for a completely different reason. We say that Hubble's law is not applicable at such small scale, but out of interest, if you do these kind of calculation and it turns out that, oh, you are getting the correct answer, but by wrong assumption. So such things also happen, and these things, I'm sure, gives good confidence to teachers when you're trying out new things. Okay, and then of course there are teacher groups where you can interact with these kind of questions, and ultimately the discussion among the teachers for applying new ideas also should happen. So that is where I end my session. Thank you.
Okay, so can I take some question from the chat box? Yeah, there is one question asked by Mr. Vikram Verma. Please explain the conversion of power of temperature from power 4 to 2.
That was a typo error which I corrected.
I can't see any more question in the chat box. So thank you so much, sir, for sharing your wide spectrum of knowledge and enlightening the audience with such a wonderful lecture by putting a lot of examples, real life example, I can say. So thank you so much, sir, for giving your precious time to us.